Anyway, let's get started. Artificial neurons, a brief glimpse into the early history of machine learning. Before we discuss the perceptron and related algorithms in more detail, let us take a brief tour through the early beginnings of machine learning, trying to understand how the biological brain works in order to design AI. Wherein Cullen and Whitehead published the first concept of a simplified brain cell, the so-called Macaulay-Page neuron, in 1943. The logical calculus of the ideas emanates in neurons activity. Neurons are interconnected neural cells in the brain that are involved in the processing and transmitting of chemical and electrical signals, which is illustrated in the following figure. Collins and Page described such a nerve cell as a simple logical gate with binary outputs. Multiple signals arrive at the dendrites, are then integrated into the cell body, and if the accumulated signal exceeds a certain threshold, an output signal is generated that will be passed on by the axon. Only a few years later, Frank Rosenblatt published the first concept of the perceptron learning role. Based on the MCP neural model. With his perceptron role, Rosenblatt proposed an algorithm that would automatically learn the optimal weights coefficients that are then multiplied with the input features in order to make the decision of whether a neuron fires or not. In the context of supervised learning and classification, such an algorithm would then be used to predict if a symbol belongs to one class or the other. The former definition of an artificial neuron. More formally, we can put the idea behind artificial neurons into the context of a binary classification task, where we refer to our two classes as one positive class and negative class for simplicity. We can then define a decision function. Let's say it's I don't know how to read it, but wait, let me check it out. Well, it's kind of like this symbol, so I would call it phi. Okay, let's say a decision function phi that takes a linear combination of certain input values x and a corresponding weight vector w, where z is the so-called light input. Z equal to w1 times x1 add w2 times x2 and so on until Wn times x sub n. And we can represent that vector as this. If you are familiar with MATLAB, you'll say it as a vector. Or if you are familiar with Python, you'll say it as a list. It's the same thing. Now, if the light input of a particular symbol xi is greater than a defined threshold zeta, it's zeta, for example, you can say it here, theta. Okay. We predict class 1 and class negative 1 otherwise, so it should be 1 or negative 1. In the perceptron algorithm, the decision function phi is a variant of a unit step function. Phi z, function phi z equal to 1 if z is greater or equal to zeta. The function phi of z equal to negative 1 if z less than zeta. For simplicity, we can bring the threshold zeta to the left side of the equation and define a weight 0 as w sub 0 equal to negative zeta and x sub 0 equal to 1, so that we write z in a more compact form. Okay, here this equation transportation is not difficult to understand. And you say x sub 0 equal to 1, so this in writing here should be just w sub 0, and w sub 0 equal to negative zeta. So when we put the negative zeta to the right, you will say something like this, say greater or equal to zeta. Okay, when he brings that threshold zeta to the left side of the equation, that function could become something like this. When function phi of z equal to 1, z greater or equal to 0. Otherwise, if z less than 0, this phi function will get negative 1. In machine learning literature, the negative threshold or weight w sub 0 equal to negative zeta is usually called the Bayes unit. In the following sections, we will often make use of basic notations from linear algebra. For example, we will abbreviate the sum of the products of the values in x and w using a vector dot product, whereas subscript stands for transpose, whereas superscript 商标 T stands for 代表了 transpose 颠倒 which is an operation that transforms a column vector into a row vector and vice versa. Okay, this T means an operation that transfers a column column vector into a row vector， 就把竖着的一列数变成横着的一列数。Okay, we will see that. For example, 1, 2, 3 multiple 6, 5, 4, 5, 6 equal to 1 times 4, 8, 2 times 5, 8, 3 times 6, and equal to 32. Furthermore, the transpose operation can also be applied to matrices to reflect it over its diagonal. For example, in this book, we will only use very basic concepts from linear algebra. However, if you need a quick refresher, please take a look at this course. The following figure illustrates how the light input ZL equal to W superscript T X is squashed into a binary output -1 or 1 by the decision function of the perceptron, and how it can be used to discriminate between two linearly separable classes. Okay, we know that T stands for transpose. And if you are familiar with mathematics, you will notice this wave function is actually result y, and the y only got two values, 1 and -1. And the input data is w transported w times x, and the right figure is another graph that shows the right points represents those results less than 0, and the blue points represent those things greater or equal to 0. The perceptron learning rule. The whole idea behind the MCP neuron and Rosenblatt's thresholded perceptron model is to use a reductionist approach to mimic how a single neuron in the brain works. It either fires or it doesn't. Thus, Rosenblatt's initial perceptron rule is fairly simple and can be summarized by the following steps. 1. Initialize the weights to 0 for small random numbers. 2. For each training sample x, compute the output value y. Update the weights. Okay. I said I feel shame that I couldn't able to understand those math meaning. I haven't learned it before. That's a shame, I guess. Maybe that's also why I can't master or learn AI for so many weekends or months. I don't know. Here, the output value is the class label predicted by the unit step function that we defined earlier, and the simultaneous update of each weight W sub j is a weight vector W. In the weight vector W can be more formally written as S. The value of data W sub j, which is used to update the weight Wj, is calculated by the perceptron learning rule. Okay, this rule, I don't know how to say it. Where the eta, I think maybe it has a meaning of sum, where eta is the learning rate, typically a constant between 0.0 and 1.0. Y subscript I is the true class label of the I's training sample, and Y bar subscript I is a predicted class label. It is important to note that all weights in the weight vector are being updated simultaneously, which means that we don't recompute the Y bar subscript I before all of the weights at W are updated. Concretely, for a two-dimensional dataset, we would write the update as the following. Before we implement the perceptron rule in Python, let us make a simple thought experiment to illustrate how beautifully simple this learning rule really is. In the scenarios where the perceptron predicts the class label correctly, the weights remain unchanged. However, in the case of wrong prediction, the weights are being pushed towards the direction of positive or negative target class. To get a better intuition for the multiplicative factor x, let us go to another simple example here. Let's assume that x sub j equal to 0.5, and we misclassify the sample as negative 1. In this case, we would increase the corresponding weights by 1. So, the light input x times w would be more positive the next time we encounter that sample, and thus be more likely to be above the threshold of the unit step function to classify the sample as negative 1, as positive 1. Yes, of course. The weight update is proportional to the value of x. For example, if we have another sample x sub j equal to 2, that is incorrectly classified as negative 1, it would push the decision boundary by an even larger extent to classify this sample correctly the next time. It is important to note that the convergence of the perceptron is only guaranteed if the two classes are linearly separable and the learning rate is sufficiently small. If the two classes can't be separated by a linear decision boundary, we can set a maximum number of passes over the training dataset epochs and a threshold for the number of tolerated misclassifications. The perceptron would never stop updating the weights otherwise. OK， 首先他说这个 perceptron， 感觉好像是那个截距还是什么鬼的英文单词，他这里翻译成感知，我也不知道。首先他讲你要用这一个方法的话，首先这一个东西必须是线性可分割的。如果非线性这个缠在一起的话，那就不能用这个方法。毕竟它这一个公式也是一个线性的公式，肯定只能这样。Now, before we jump into the implementation in the next section, let us summarize what we just learned in a simple diagram that illustrates the general concept of the perceptron. Okay, fair enough. We get those input basically just x and weight, yes, weights, and we put it together to the light input function to do some calculation, for example, to get the sum of it, and then we use a threshold function to determine the result is 1 or -1. Okay, it's a binary result. And by doing so, if we know what the result is, we could check if we get it wrong. If we get it wrong, we have to update the weight the next time. Okay, if we get it right, okay, we remain those weights. So it's a dynamic processing. The prostating diagram illustrates how the perceptron receives the inputs of an sample X and combines them with the weight W to compute the next input. To compute the lat input. Lat input is then passed on to the threshold function, which generates the binary output, -1 or +1. The predicted class label of the sample, just two different classes, -1 and +1. During the learning phase, this output is used to calculate the error of the prediction and update the weights. Okay, fair enough. I'm gonna say next time I'm gonna do this. And for somehow I decided to write those codes by myself. I will not do some copy and paste the job. I'm gonna type it hand by hand. So if anything goes well, I will see you in the next video and week, and we will be focused on this book, because I know if we don't do so, we will never really learn AI. So that's the work we're gonna do next. And I hope you enjoy today's video, and